Hello, this is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Differentiation Tradecraft Theorems 1. Make sure to actively engage in this material. The method that we used for computing the derivative of a function based on the limit definition was we started with a difference quotient like this and then evaluated the limit as h went to 0. And as you probably observed, this method is tedious even for relatively simple functions. It is important to keep in mind, though, because calculus is the study of limits. In this section, we're going to begin deriving certain rules, proving theorems, that will simplify the finding of the derivative of a function. This notation we're going to be using. The derivative with respect to x of f of x, and that's read d dx of f of x, means the derivative of f with respect to x at x. First theorem is the derivative of a constant is equal to 0. A constant never changes. So the derivative with respect to x of a constant, where c is a constant, is equal to 0. Now that lines up with the idea of this being the slope of the tangent line, because if f of x is equal to a constant, it's a flat line. That means the slope is 0. And so that certainly is true. If you go back to the definition, you say f prime is equal to this limit, but this is always c, so you get 0. Here's an example for you to do. Find the derivatives of this function and this function. Actually, it's two examples. You know what to do. Let's see how you did. So the derivative of 28, it's a constant, so that is 0. Pi squared is a constant. It is near 10, and so when you take the derivative of the constant, you get 0. Here's another theorem, maybe a more involved one. If n is any real number, the derivative with respect to x of the function x to the n is n x to the n minus 1. So you take the exponent, you multiply by it, and you reduce the power of the exponent on the x by 1. Now, it can be algebraically involved to prove this for any real number, but let's just talk about what it is when y equals f of x equals x squared to provide some insight. So the derivative is going to be the derivative of that, so that is equal to, by this, the limit as h goes to 0 of f of x plus h minus f of x, all by h. So we do that with f of x equal x squared. We expand this and subtract off the whole of f of x. The x squared will cancel, and we can factor the h out of what remains. And then we cancel the h, as we've done many times, and we get the answer is 2x. So you see it was x squared, so it's going to be 2x to the 2 minus 1 is 2x, as we set out to show. To differentiate a function whose rule involves a radical, it's best to first rewrite the rule using fractional powers, and that makes it easier to differentiate using this rule. Okay, so here is an example 2. There are 3 problems for you to do. You know what to, are you going to take the derivatives? You know what to do. Let's see how you did. So here, this is x to the 1. So it's 1 times x to the 1 minus 1. That's 1 times x to the 0, and x to the 0 is known to be 1. If y equals f of x is x to the 8th, it's going to be 8x to the 7th. And if f of x is equal to x to the 5 over 2, then the derivative is going to be 5 over 2 x to the, you subtract 1 from 5 over 2, that means you're subtracting 2 over 2, so you're left with 3 over 2. Yes, there are fractions. Here's another problem for you to do with radicals. You're to find the derivative of the following functions. There are 2 here. You know what to do. Let's see how you did. So we're finding the derivatives of these. Now the square root of x is x to the 1/2. So this is going to be 1/2 x, and we subtract 1 from 1/2, we get minus 1/2. And x to the minus 1/2 is 1 over x squared. And so we could write it this way or this way. In this case, this is in the denominator, and the cube root is x to the 1/3. So this is x to the minus 1/3. So when we take the derivative, it's going to be minus 1/3 times x, and we're subtracting 1 from this. Now when you subtract 1, you're subtracting 3 over 3, and that means this is going to be minus 4 over 3, and I can write it this way, or I can put it in the denominator. Please, in your notes, make sure you know there's a minus there, and that's also a minus. There's some other rules. This is one. For the rest of these rules, we implicitly assume that f and g are differentiable, so these things make sense. So this is the derivative of a constant multiple of a function. So if you have a constant times a function, you can pull the constant through the derivative. So the derivative with respect to x of c times f of x is c times the derivative with respect to x of f of x. Now you see this comes very easily because this was true for the limit. The limit of a constant times a function is a constant times the limit of that function, and since the derivative is a limit, this is almost automatically true. Here's how you might say it in the words. The derivative of a constant times a differentiable function is equal to the constant times the derivative of the function. And if you do the calculation, you get this, and you see we are, in fact, using the property of limits, pulling that through, but then this is the derivative. You don't have to memorize the proof, but you do have to use the result. So here are 2 examples called example 4 for you to do. You know what to do. And we will continue this in the next video, and we'll see how you did.